Okay, so we'll go back to another video. Here's a nice little limit that we have of both a base function and actually also including the trigonometric function as well. So a combination of all that, we have the limit as x approaches 0 of a to the power x minus a to the power sine of x divided by x cubed. And also keep in mind that we are looking at a is strictly greater than 0 for all the reals. So I want you to guess how many times we're actually going to be using L'Hopital's rule in the comments below before we actually start doing this. So yes, that's actually basically what we're going to be doing here for evaluating this limit. So as you can already tell that if you were to plug the limit first, you can already see that it's in a 0 over 0 indeterminate form. So of course, that being the case, we have to apply L'Hopital's rule. But actually, as you notice, as we keep going on further and further and further, this cycle repeats over and over and over, and hence that's why there's a little I'm supposed to play a little guessing game on how many times we actually use that rule. So again, that's all that needs to be said. Everything is all strictly just L'Hopital's rule. So if you know your derivatives, know how to handle deriving anything with the log base, well, with the base, and then with the trigonometric functions and all that stuff all together, then we're pretty much clear from there. So with that, why don't we just jump right in? So capital L, I'll just call that. So as you can tell, as mentioned, if you just plug in x for 0, everything is going to be in the 0 over 0 indeterminate form. So with this being the case, let's actually now take the derivative of our numerator and denominator. So that means if I take the derivative a to the x, so in respect to x, of course, so that means that's going to be a to the power x and then times ln of a. And then we have a to the power sine of x, which is going to be a to the sine of x times ln of a. And then don't forget to take your derivative of the exponent, so times cosine of x, all this being divided by 3x squared. Okay, and then if we just plug in the limit x approaches 0, guess what? This thing is going to be, of course, a 0 over 0 indeterminate form. So just like that, we're going to have to yet again apply L'Hopital's rule a second time. So that means if I were to, and don't forget, the 3 can actually be factored out outside. And you'll also notice that everything is ln of a, the constant, so I can actually factor that outside of our limit. So ln of a, and then divided by 3. So then our limit as x approaches 0. So then we have to yet again take the derivative of both our numerator and denominator. So then basically I have ax and then minus ax, or not x again, sine of x, and then times cosine of x. And then next thing is, of course, so that means ln of a, and then divided by 3. Then the limit as x approaches 0. So we got to be careful here because we have to actually take our derivative of our numerator, because we have the product rule we're going to have to apply carefully. So first I have a times to the power x, and then times ln of a. Then of course we have to apply the product rule over here. So we want to be super duper careful with this. So this would be So this one will be a to the power sine x multiplied by ln of a, and then multiply its derivative, which is cosine of x. So that means this will be cosine square of x, and then product rule. So this will be the same, and then take the derivative of that. So that means that will be subtract sine of x, and then times a to the power sine of x. And then all with the denominator, this is simply just going to be 2x. Okay, then of course, we'll have to put everything, plug in as it approaches 0. That's going to be 0 on the denominator. So let's see, this is going to be a times a, so there's 0, and then, yep, this entire thing will of course simply just be 0. So that means this is of course yet again another 0 over 0 indeterminate form. So then to continue forward with this, so that means I can take the 2 outside, so that it's just divided by x, and divided by x, and then if I take its derivative after applying the L'Hopital's rule, that's just going to be 1, so at least that'll disappear. So then that means I have the limit as x approaches 0. Now we just have to take this entirety of its derivative. So that means if I take the derivative of this is going to be ax and ln of a. That's still going to be square, so that means a to the power x, and then times ln of a quantity square. Okay, and then here's a long one. So of course, everything is going to be in terms of the product rule yet again. So we have to be careful on how we derive this. So to put everything together, I have cosine of x. So you can actually take this one step at a time just to, follow through. So cosine of x, then times a to the power sine of x, add this with a to the sine of x, multiply by ln of a, and then times sine of x times cosine of x. And then still we have to consider the natural log, so that means now we have minus ln of a, and then multiply by cosine cube of x multiplied by a to the power sine of x times ln of a, and then subtract a to the power sine of x, and then multiply by sine of 2x, just from placing one of the identities we actually just do from there. Okay, so pretty much that's that long identity. So now we can simply just let x approach 0, and so by doing so, that means I have ln of a divided by 6 right here. Then put everything as it approaches 0 over here on this line. So then this is just going to be ln a quantity square. Add this with 1, and then subtract 0, and then subtract ln of a, then multiply with ln of a, subtracting 0, close that off, and you'll notice that 0 and then 1, the ln a squares are going to cancel each other out, so simply the final answer is that the closed form is going to be ln of a divided by 6. And just like that, we have found our nice little closed form for this our limit over here evolving. So let's see, that's actually 3 times we've actually used L'Hopital's rule. 1, 2, and then 3. So if you counted 3 times, congrats. You didn't win anything. It was just, just for giggles. But yep, 3 times we used L'Hopital's rule to expand this ginormous of an expansion of the, the limit after applying L'Hopital's rule. So I'm doing that, and then once simply you just had that denominator disappear, then we can simply just plug everything for 0 over here, and then we get this result to come out of this form just like that. So yeah, that's pretty cool if you ask me.